In this lecture, we will be looking at carboanions. Carboanions. In the last lecture, we looked at the reactions of carbocations. Notice the difference. Carbocations were positive, and now we'll be looking at carboanions. And as we'll see, they are negative with one more electron compared to the carbon atom. So in this presentation, what we will be looking at is essentially the structure and stability of carbocations. Next, we will be looking at the generation of carboanions. How are carboanions actually made as intermediates? And then lastly, we will look at the reactions of carboanions. Okay, so let's begin. Carboanions, as I mentioned, are anions, which means they're negatively charged. Just a quick review here. You will recall that carbon has 6 electrons in the atom, which makes it neutral. Here we have the 7 electrons because we have a carboanion. In terms of the structure of the carboanions, let us imagine that we have our 1s orbital that's unhybridized. So let me refresh your memory with the electronic configuration of carbon. It's 1s2, 2s2, and 2px1, 2py1, and 2pz0. So we have 2, 4, and 6. Of course, since the 2p orbitals are degenerate, these 2 electrons here could be in any of the 3 2p orbitals. To explain the observations that are made experimentally about carboanions, this model is used. So we have our 1s orbital that's shown here, but what's happening here, we'll have to hybridize all of these orbitals here, the s and the 3 p's. So if you hybridize or mix, we get sp3 hybridized orbitals. Since we have 7 electrons, we have to put them in 1, 2, 3, 4, 5, and of course the 1s still has 2 electrons, so we have 7 electrons here for the carboanions. You'll notice, however, that there are 3 bonds to the carboanion, 1, 2, and 3. So an orbital a bond can be made here to another carbon or hydrogen. Here, 1 electron shared from another atom, such as carbon or hydrogen, to form a bond. Same here to form a bond. So that would be these electrons right here. And the 2 electrons here are in the sp3 orbital. Notice the geometry. The geometry of your sp3 is tetrahedral, but because we now have just 3 atoms bonded to this carbon and a lone pair of electrons, the geometry now assumes a pyramidal geometry, much like ammonia. So if you remember, the geometry of ammonia is pyramidal, where the lone pair of electrons on the nitrogen is in an sp3 orbital. Same for the carboanion as shown here. There are other possibilities of putting a pair of electrons on carbon that are not on carbons that are not sp3 hybridized. So let's look here at the other possibilities. So here we have the sp3 hybridized carbon. How do we know? Because we have 1, 2, and 3, and of course a fourth orbital, which makes sp and 3. You may recall that's 1 s and 3 p's. That makes to get sp3. So this is your sp3 carbon. But it's possible to have the vinyl carboanion. So here we have a carbon, and it only has 1, 2 bonds to other atoms, and the unpaired electrons will be in an orbital. This would have to be an sp2 hybridized carbon right here, in which the electrons are in an sp2 hybridized orbital. Let's look at the acetylenic carboanion, which is the carbon of a carbon triple bond right here. You will recall this carbon here is sp. So the electrons here are in an sp orbital. As we'll demonstrate in the next slide, the electronegativity of the carbon increases to the acetylenic carbon. Remember, electronegativity here is a tendency to pull electrons towards itself. Tendency to pull electrons towards itself. So it implies that this carbon here is more electronegative than this one, and more electronegative than this one. Let's see why on the next slide. Your sp3 carbon only has 25% S character. sp2 carbon has more S character, which is 33. And of course here you will recall that the acetylenic carbon, or the sp carbon, has 50% S. Why are we emphasizing the S character? Because you will recall from your general chemistry course that the protons are in the nucleus, and the s orbitals are closer to the nucleus in terms of its spherical nature, at least compared to the p orbitals. So if the s orbitals are closer to the nucleus, which are positive with the protons attract electrons. So the more S character there is, the more electronegative will be that atom. Okay, let us look at carboanions that have pi systems on adjacent atom. Is it still sp3? So as you can tell, here's a benzylic carbon. It's bonded to 2 other hydrogens and to the phenyl ring. So it looks like there are 3 bonds here. So it should be sp3, where these electrons are in an sp3 orbital, and you would expect it to be pyramidal. However, due to the resonance that can be achieved by delocalizing these electrons here into the benzene ring, this carbon here achieves a sp2 character. We say it's planar because we have electrons delocalizing throughout from the benzylic carbon. This is the benzylic carbon into the ring, which means that it has to be flat, planar, which would imply that this carbon is now sp2. So if there is a carboanion adjacent to a conjugated system, a pi system, more than likely it will rehybridize to get your sp2, so that delocalization can take place. On the other hand here, very similar carboanion, but no conjugation here. So we would expect this to be pyramidal, and the charge here is localized, which means that these electrons are right on that carbon. They'll not be delocalized as shown here, and that would be pyramidal here, and this would be flat. Let us look at an evidence why we think that carboanions are sp3 and pyramidal, and if it's adjacent to a pi system, it's flat. So here's an experiment here. So if we have BuLi here, which will actually take off the bromine and create the carboanion right here. We'll see in a second how that's done. But the electrons are right in here because they're bonded to the very electropositive lithium. So here's the anion. If this anion is sp3 with these electrons here in a sp3 orbital reacting with carbon dioxide, you may recall carbon dioxide is this. So it would react right here to give this product its 100% retention, which means that these electrons are right here in a pyramidal sense, and reacting with carbon dioxide gives the retention here. Retention, of course, is from this starting material. So the stereochemistry here is retained because of this pyramidal carboanion. Let's look at this one. So in this case, we will replace this methyl group with a CN. So that's C triple bond to an N. Notice the pi system. Same reaction here to create the carboanion right here and lithium here. But because it can have resonance with this C triple bonded N that's adjacent here, so in other words these electrons can come in, we will get here a planar carbocation. So this carbocation is flat because the electrons are in conjugation with this pi system here. Let's see if we can do it. So we can draw this out here, and these electrons come onto the nitrogen. So you can see delocalization right here, which means that it's flat or planar. Same reaction with carbon dioxide followed by hydrolysis gives us a racemic mixture, which means that its retention 50% and inversion would be the other 50%. So this is clear evidence that a localized carboanion is pyramidal, and a carboanion that's delocalized because of adjacent pi system is planar and gives us this as a product, because attack can take place from either end of the flat carboanion. Let us look at the structure and stability some more here. So we're looking at the synthesis here, but let's look at the structure. So carboanion is really a carbon that's bonded to a metal. So if you look at your periodic table, you'll see the alkali and alkaline earth metals to the extreme left of the periodic table. You may recall that atoms to the extreme left of the periodic table are in fact very electropositive, want to give up electrons, and atoms to the right are electronegative. So you'll see from the periodic table that now carbon is more electronegative if bonded to M, which is a metal or which is an alkali or an alkali earth metal. So in this case we have a bond from carbon to metal to M metal, where this is partially negative because carbon is now more electronegative than M. So we have this. But we can put here the negative charge on carbon and the positive charge on the metal ion. Of course, as we'll see later on, the metal ion, if it's very, very electropositive, we have more of an ionic bond, just like sodium chloride. But here we have carbon negative M plus. And if the metal ion is not as electronegative, it's more of a polar covalent bond where this carbon here is partially negative. Here's some examples. Lithium, extreme left of the periodic table, so you'd expect this to be R partially negative. In fact, it's considered to be ionic where it's R negative and Li plus. Organolithium. Here's the organomagnesium. Magnesium is one more over in the column from lithium and one down, so it's not as electronegative because it's one over to the right and one down, so it's not as electronegative as lithium. So you would expect this bond here to be not as ionic as over here, but still carbon is more electronegative than magnesium. You will recall this is the Grignard reagent. Here's another one, organocuprate, known as the Gilman reagent. This time the carbon is bonded to copper, and you'll see from your periodic table that copper is now in the transition, which is much closer to carbon but still more electropositive than carbon. In other words, carbon is more electronegative than copper, so you'd expect this bond here to be even less ionic and more polar covalent compared to your Grignard and your organolithium. So these are examples of organometallic reagents in which there is a carboanion or a carboanion-like species as part of this structure. Let us look at the generation. How do we make these? They are essentially made by the insertion of the metal into a carbon halogen bond, alkyl halides. So if you have R, X here's a halogen such as chlorine, bromine or iodide, the fluorine bond is just too strong, you can insert your lithium right in here, and as you can see here we have the RLi. Of course this will break to give Li plus. So this is your organolithium. Just to show you how the Gilman reagent is made, the organolithium, if react with copper, the copper can insert itself right in the middle here. So we have organocuprate right here, and that's the Gilman reagent. Let's look at this one, because this one we're more familiar with, and this is the Grignard reagent. We use this a lot in undergraduate organic chemistry. So here we have Rx. Again, X can be chlorine, bromine, or iodide. Magnesium can insert right in here to get your organomagnesium, which is known as the Grignard reagent, where this is partially negative or considered at times to be ionic because of the difference in electronegativity between the carbon and the magnesium. Since magnesium is divalent, it has the other halogen bonded to it. Here's a specific example of synthesis of the Grignard reagent. You take Grignard, bromobenzene for example, magnesium in ether. The trick here is to have this extremely dry. The magnesium inserts right in here to get your phenyl magnesium bromide, or the organo metal reagent here, or the Grignard reagent. Okay, let's look at another way to generate anions. And this is essentially an acid-base reaction. So here, let's look at the carbonyl here, or in this case, this is a ketone. We have R and R. But you should notice that this is the alpha carbon, so therefore these are the alpha hydrogens. They are acidic, so if you have a base here which has an unshared pair of electrons, you will recall that a Lewis base is a Bronsted base is a proton acceptor. So this base here can pull off one of these hydrogen as a proton. Notice it's pulling it off as a proton, and these electrons come onto your carbon to get this, and of course your conjugate acid from the base. This is your carboanion. Pardon me, this should be carboanion. I'll make that correction on the PowerPoint. So here is your carboanion, resonance stabilized. It's also referred to as an enolate. As you can see, here's an ene, and the salt of the enol. So it's an enolate. So here's resonance stabilized, but the bottom line here is that the negative charge, or the unshared pair of electron, resides on the carbon. But it's resonance stabilized, as we'll see, as we saw earlier, because of this conjugated system adjacent to it. So you'd expect this carbon here to be sp2 and flat, and here it's more looking like sp2 and flat. But the bottom line here is that the enolate is a carboanion, and it's resonance stabilized as shown here. Here's an example of how we can actually make it, a more specific example. So here's acetone, here's a carbon here, and alpha hydrogen, acidic. A weak base such as OH, so sodium hydroxide or potassium hydroxide, can pull this off to get the resonance stabilized enolate anion. But as you can see here, the equilibrium here, K, is to the left. So in other words, you just get a small quantity of this, and the majority will exist here. Of course, as you will recall from your undergraduate organic chemistry course, you can drive the equilibrium to the right if you take off water. It's called Le Chatelier's principle. So if you evaporate water off, the equilibrium shifts to the right. One thing I want to point out here, though, that the pKa of these hydrogens here are around 20. And after the reaction is done, the pKa of the conjugate base, the conjugate acid of this base here that abstracts this hydrogen, is 15. So the equilibrium tends to shift to the pKa that is higher of the conjugate acid. So you can see here the pKa is 20, so the equilibrium shifts to the left, or lies to the left, I guess is a better term. So the pKa here is 20 high of the conjugate acid here, so the equilibrium lies to the left. But look at this one, pKa here, same pKa, same acidic hydrogen, but now we're using LDA, lithium diisopropyl amide, as shown here. So lithium diisopropyl amide, this is the amide anion, an extremely strong base because its conjugate acid has a pKa of 35. So therefore this equilibrium here, K, lies all the way to the right and not to the left, as shown here in the top reaction. Again, so the equilibrium will lie in the direction of the weaker conjugate acid. Here's the acid, 35 to the right. Here's the acid, pKa 20 equilibrium to the left. So again, whenever you need to generate your enolate by this method, it's best to use a very strong base such as LDA to get a maximum amount of your conjugate base here, or your enolate, or your carboanion. Let's look at another example of generating carboanions. So in some cases, the organometallic can react with an alkene. So we have an organometallic reagent reacting directly with an alkene. So here's our organometallic. Remember again that this is carbon that's bonded to lithium. So in essence, we have here the anion here and the cation here. We tend not to write it as negative and positive because it's not really 100% ionic. But these electrons here can interact with this final, or the double bond, and these electrons come over here. So here we have our carboanion, which basically is generated from a carboanion reacting with an alkene, as shown right here. Again, carboanion right here. Let's look at some more examples here. Here's a Gilman reagent, organocuprate. Here is a double bond, but it's in conjugation here with a carbonyl. But still yet here is the alkene portion, known as an alpha beta unsaturated. Why alpha beta? Alpha carbon, first carbon from the carbonyl, and beta. So the alpha beta unsaturation is right here. So as you can imagine, these electrons here from the anion can interact right here, and of course these electrons can come in here to create your carboanion right here. Of course, as you can imagine, that's resonance stabilized again, but the bottom line is it is a carboanion. Here's another example. Gilman reagent. This reacts here, alpha beta unsaturated ketone in this case. This reacts right here to give the carboanion here. You may be wondering, why not here to give the carboanion here? You can see that if the carboanion is here, it is a localized carboanion, not as stable as a delocalized carboanion, as we can see here. These are delocalized enolate carboanions. So again, remember that there are possibilities, but the most reasonable one typically gives the most stable intermediate or carboanion in this case. Let us look at another example here. Here we have an inorganic anion, such as a sulfide, negatively charged. But look at this reactant here, organic, but it has nitro groups bonded to it. Remember, the nitro group here is N, so it would be N, O, and O, and of course it has a charge. So it's electron withdrawing, so it's pulling out all of these, well, it's pulling out the electron density from the ring. So the benzene ring here is very electron deficient because of the nitro groups that are bonded to the benzene ring. This is very reactive, so as you can imagine here, electrons can come in and form an resonance stabilized anion as shown here. So this is another mechanism or method of generating carboanions, in which we have an inorganic anion reacting with a very electron deficient organic molecule to get an anion as shown here. And of course, just to emphasize, the driving force for this reaction is that the benzene ring here is electron deficient. It would not happen if it did not have so many electron withdrawing groups bonded to the benzene ring. Okay, let's look now at reactions of carboanion. One, of course, as we said, is an acid-base reaction because carboanions are in fact bases. You may recall that a base is an electron pair donor, Lewis base, or a Bronsted base is a proton acceptor. So here we have this molecule here, we have our alpha hydrogens here, we have sodium methoxide here, a strong base. Remember, this is O and plus, so it can take off one of these hydrogens here to form the anion right here, as we have seen before, in the presence of a solvent such as deuterated methanol and deuterated water. It can abstract, and in fact will abstract, the deuterium, because the deuterium in this case is acidic. Not very acidic, but acidic enough that the strong base here can abstract it to get here CD3, and eventually it will continue until all the acidic hydrogens here, or all the alpha hydrogens here, are replaced with the deuterium, because we have the enolate that's formed. Enolates are also good nucleophiles. Remember here, nucleophile is a nucleus-loving species, a species that loves positive. So in other words, here we have a nucleophile. It must have an unshaped pair of electrons, which it does. So we can see here that this LDA is a strong base, so it's going to take off one of these hydrogens here to create the enolate, or the carboanion as shown here. This carboanion has an unshaped pair of electrons. It's nucleophilic, and in the presence of an electrophile like here, these electrons can come right in here and of course do a substitution reaction to get that as a product, and of course the other product is lithium bromide, a salt. So this becomes the organic product. So enolates or carboanions are also good nucleophile in addition to being strong bases. Okay, let's continue here with our reactions here. So in this case, rearrangement of carboanions are not as frequent or are observed as frequently as rearrangements that were observed for carbocations and radicals. You may recall, especially for carbocations, there were possibility of numerous rearrangement. Here it's not as common, but here's an example. Here we have here an alkene, and of course we have our negative charge right here, our carboanion, and this is the plus. You can see here that this hydrogen can migrate over to here and put this as the carboanion right here, and of course if it's right here it will delocalize with this other pair of electrons as shown here. So you can see that this hydrogen here is now over here, this carbon, and of course rearrangement to give this. Here's another possibility. Again, remember whenever we write here RLI, this is really the anion and this is really the cation. We tend not to write it like a salt, as I mentioned earlier, because it has some covalent character to it, because it's not strictly ionic, such as sodium chloride. But as you can see here, these electrons can come over here, and these electrons go over here to form here that. So that's rearrangement to give from this carboanion to this carboanion, just to emphasize again, here are now our unshared pair of electrons, negative charge, and here is our lithium plus. Another example here, we can abstract this hydrogen here as a proton using a strong base such as BuLi, butyl lithium, or LDA if you prefer, to create this anion right here, a carboanion right here. Notice the structure here, cyclopropane ring here, but it can rearrange to give this, as shown with these arrows. Notice the driving force for the rearrangement is that this is aromatic, which means, as we'll see, or you'd know that this is aromatic because it has 6 electrons in a ring, etc., etc. It meets Huckel definition of aromaticity. So this is a rearrangement of the carboanion from here over to here. Don't forget again, this is the negative and this is the cationic portion. So that's rearrangement of carboanions. Let us conclude by looking at a well-known reaction. It should be an N. I'll correct that before I post the slides. So well-known reaction here is the Furvoski reaction. It proceeds through carboanion intermediates. So a good question that's often asked is, for the Furvoski rearrangement shown below, provide a step-by-step mechanism to account for the observed products. Use the arrow formulism to show electron movement. So in other words, how does this reaction work? In other words, how does it get from reactant with this as the reagent to give this as a product? Close examination of this shows that, of course, the chlorine leaves, but this is a 6-membered ring here, and we have a 5-membered ring here. So obviously there's a ring contraction. So you can imagine here there's going to be some rearrangement of the carboanion intermediate. The next slide shows the actual proposed mechanism. So here we have a strong base, sodium methoxide. As you can imagine, methoxide anion is a strong base. Here we have an alpha carbon which has 2 alpha hydrogens, fairly acidic. It pulls that off to form the anion right here. As you can see here, it's the anion. Good leaving group, so we have a substitution reaction here to form this. Here's where the ring contraction takes place, because you can see a 5-membered ring right here after this takes place. The OCH3 comes in to this electropositive carbon here because it's bonded to a very electronegative oxygen to give this. When these electrons come back in to form the double bond, why does it come back in? Why do they come back in? They come in because it wants to form the double bond. Remember that the oxygen carbon double bond is a very favorable strong bond in organic compounds. Once they come in, we get this, the anion is right here, and of course in a solvent it picks up the acidic hydrogen, or it's strong enough a base to pull off this proton here, this hydrogen as a proton, to get our proposed molecule. So here we can see this is the mechanism for the proposed mechanism for the Furvoski reaction, or the Furvoski rearrangement. As you can see here, the anion is created through a substitution reaction, and intramolecular substitution, we get this, and a rearrangement, we get this as our product. So this is the end of, yes it is, the end of this lecture on carboanions. Continue reading upon this carboanions. Our next lecture will be on electron deficient species, which will be nitrogen, electron deficient nitrogen, and electron deficient oxygen, which I'll get organized and post in the week, definitely in the week, and send you an email. Okay, bye.